Hello and welcome back. Okay, so I've got the Uart here. Now the FIFO buffers we converted to PCB quite early, but the rest of the Uart here is still taking up breadboards and I want to free all of this up. I've got a couple of good breadboards here and I've got a better use for them. So I'm going to go and do the EDA work necessary to turn that into a PCB and see how far we get today. And just as a reminder, I've got the Uart version of the prime number finding code. So for a while this was my only I/O from the processor. This can go at quite a reasonable rate. At the moment I've still got the 25 megahertz crystal divided down to 3.14 megahertz going at the moment. Now if you're new, I do have a whole series of videos in which I've been building up this Uart serial port from the ground up. So this video is really just going to be about transcribing this work onto a PCB. So if you actually want to get an understanding of what this circuit's doing, you'll be better off going and watching the earlier steps in the video series, which I'll provide a link to in the description. Let's get on with it. Okay, let's see where we got to. This is the 18.5 megahertz crystal. So this is the receive circuit as it was before we added the FIFO. This line triggers when we have a received byte. This is where the data appears. So we need to get the control lines for our FIFOs. Right, I'm going to prefix all the lines with RF for the read FIFO. Now for the read FIFO, data out we're going to map straight to the main bus. So it's only actually data in we need to worry about. Now with the FIFOs on the back plane, I want to fit them like that. I don't know how tall the Uart needs to be, but I want to make it the width of the two FIFOs. I'm pretty sure we should be able to fit it into that. Alright, so we want all of those on the back plane as well. I think we'd best rename this. So I'm basically doubling up most of these because we need to use them for cross connections. Right, so there's the main bus connections. I like the idea of that being a really simple connection. I think these are misnamed. Be good to get the receive over here and the transmit over here and the status in the middle. So 11 and 12, what are supposed to drive the Uart? Actually, we might get away with a lot less connections into the Uart PCB than we've got here. I don't see why we can't drive reset directly from the board. Both read and output enable is the assert line for device 11. Output enable for the transmit we just pulled down low because we had that going out all the time. So that's just selective inputs into our shift register. device 11 load, we connected straight to the transmit fifos right. Right, so we've packed that all together into one place. This is the same layout as the wires we've got going into the breadboard at the moment. Let's grab another one of those. Going to need to be able to bring reset in here as well. T50 status 2. Managed to do that and leave everything in the right place, which should also mean if I change this and copy it back into the back plane, the object should update. I think we're probably going to need slightly more room than this, but that's quite close. So if we hook that signal up to the receive FIFO data write line, and we've got that hooked up already, that should be the receive working now. Now we need to start building the transmit circuit. Now this first 193 is literally a straight divide by 16 on the clock. So we take Q3 and make that the count up. Now we want master reset to be low, and we don't actually care about the data lines for parallel load because we're not using it, but we do need to take them somewhere. Ground is the obvious choice. Whereas on this one we are using the parallel load, and more importantly the data is used to control the number of ticks we do between data frames. So we got this set to 11 on the breadboard. Well, 0, 1, 0, 1. So that's 5, which then means 11 ticks gets us to the carry. Alright, so that's our set reset latch. That's the parallel load signal. And then the carry signal is what resets it. I have a set that was done from here. We never used this gate, so let's chop it off. One of those inputs was the clock. And we're going to create this signal called transmit data ready. So here's our 4 OR gates. So for transmit data ready, we're basically just trying to OR all of these signals together, just to see if there's a non-zero value. And then from those pairs we OR together the outputs of those and get our final result. So now we need our shift registers to actually do the transmit. So parallel load we want to activate between bytes. So that's the bit being shifted out, and the bit being shifted in here on the breadboard, we just connected that to 5 volts. Now the first 2 bits we hardwired to 1, because we hold on that between bytes when we're not sending, and we need the line to be high. Then we wire the next one low, because that's our start bit. Now I don't think we ever see these bits on the output line, but I'm going to pull them high anyway, because that's what the resting line should be. Now we're going to need another 5-point port. I'm going to deliberately leave that line disconnected, because when I'm using the USB UART adapter, I've got a 5-volt line I don't want to connect to anything, because I don't want to be bridging 5-volt rails between the CPU and the computer. So actually having a blank one that I can just use to hold that cable would be, I think, useful. That's where transmitted data comes as it's shifted out. That would have been easy to miss because the start bit is what triggers the set reset latch. Okay, I think that base circuit is done. So we've got transmit and receive. Now we check to see if there's room in the transmit buffer by shifting off the top bit of a shift left. So transmit count is at the high end of the output. Receive count is there, so we can test if there's a byte available by ANDing that with 15. Alright, so that's all our main chips and connectors. Probably want to add a couple of LEDs. Load is to transmit a byte and assert is popping a byte out of the FIFO. Those don't actually need to come into this main circuit at all. They only really need to drive the FIFOs because we've got those connected to the main bus. But we're going to bring them in here so we can stick an LED on them because that is the way. That would have been an embarrassing absence. This is the line that decrements the bytes available in the FIFO buffer for transmit once we send one. Now, since the parallel load is always pulled high and inactive on this one, I'm just wondering if it would be easier to connect the parallel load inputs straight to VCC. Might be slightly simpler to route, and I don't think it makes any difference. Now, life will actually be easier if we can move main bus up. I'm going to wish I put the receive and transmit FIFOs the opposite way around. Right, so that receive circuit is really easy. Give us a working clock. Okay, now this is a total mess, but we can clean that up. See how much better that looks. Fabulous. Feels like quite a big gap in here I'm not really using. Now that feels like a good layout. So sound goes here, and then a couple of other little modules down here. Should work. And VGA is going to have to come over here. Big thing left to do is to route this. Okay, the routing on this one was fairly straightforward. One thing I have found is the more you think about the routing as you're laying out the circuit, the more easier it gets to do. You see all the thicker tracks I'm laying down here are power and ground lines. The design rules confirm that everything's connected the way it should be, but they don't confirm that you haven't got a big long winding path between the power input and the furthest chip from it. Here I'm stitching the ground planes together, make sure I've got good connectivity, and we're done. That'll do. Let's hope it works. We have to find somewhere to put this if we don't want the label visible. Yeah, that'll be fine. So I'm going to do the same as I did with the back plane for the pipeline and the ALU. Okay, this was a longer wait than normal. For me, anyway, it was a few seconds for you. Let's avoid spoilers. I don't think I recorded it, but I also made a tiny little bridge board for connecting the main bus and power up, just to reduce the number of flying cables I've got. And making a small back plane like this just for 3 modules feels a bit wasteful, but it's an awful lot easier than trying to create all these cross connections manually. And putting it together like this means it's a lot more likely that when I make a big back plane at the end, it's all going to work. Okay, between sending this off and it coming back, I did spot a mistake I made in the silk screen. So see if anyone in the comments works out what it was. And let's hope there's no flaw in the circuit. Now it feels time consuming, but it really is worth checking the paste thoroughly at this stage. That's the decoupling caps done. This one is just a bit of power balancing, a larger value. This one on the clock line needs to be about 20 picofarad. I don't generally keep those, but I do have a book of resistors and capacitors. Well, that was fairly painless. Long time ago, I worked out the best way getting pin headers into a board straight is to poke them into a stack of free PCBs. I could solder the crystal on directly, or I could use a crystal socket. Give one of these a go. Okay, that looks pretty good. We need to solder up the back plane before we can test it though. That's just going to be a convenient little helper board. And my plan is to have a giant combined backplane eventually that merges together all of these separate components. And it's going to be really tough to put together. I may need to develop a new strategy for holding the headers in place. With so many pin headers, it's going to be very easy to miss one. One of these has still managed to tilt over a bit. That'll do. So it's the main bus connection. There's a power connection. It doesn't actually really need to be there because there's power on this one as well, but no harm. And I think we're done. I've picked green for the Uart PCBs. That's slightly confusing because my backplanes are green, but I'm thinking about a different colour for those in the final assembly. Right, I'm going to need to get the main PCB out to test this. I suppose I could test it without, but that's quite contrived and we'd be better off testing it in the CPU directly. Okay, so we're going to want to reuse that cable. Shouldn't need the bus connection anymore. And so white is transmit, green is receive. Okay, that crystal in before I forget. This little bridging board will save me a DuPont cable for the bus. Now I don't want to bridge the 5 volts between the two circuits, but I did put a non-connected one here, just so I could have it so it wasn't dangling. Be careful here, it's actually the other way around. I've got a reset connection up here as well. I don't think I've got any easy access to a reset line down this side. Take it to 5 volts for now. Power it up. Oh, nothing's exploded. It's copying. I've got no right to expect all my PCBs to work first time. And it looks like this one isn't. Oh, what am I doing? Got no fifos. I don't want to jinx it, but that looks like it's working. Let's fire it up to full speed. Okay, so that's successfully computed all the primes that fit in 16 bits, and more importantly, it's streamed it out to the console. That's outstanding. I'm really pleased with that. Okay, I don't want to jinx it by going any further, but it looks like we've got a fully working Uart here on PCB. And the thing I'm really looking forward to is being able to write some more complicated software for communicating between the processor and my PC, because this RAM module will allow me to upload some code into memory and execute it from there. So there's a bunch of software to be written before I can do that, but having a nice, stable, permanent PCB version of the Uart is going to make that a bit more practical. Now, this is in fact, the Uart is actually complete now. The fact that I've got a typo on the silk screen might make me respin this little section of it, but in terms of functioning board, that's done. So here completes the Uart series. Hope you found it interesting, and I'll see you again soon. Goodbye. Quick addendum, I realised I hadn't tested the receive as well as the transmit. So switch to something that does both. Unfortunately, it doesn't look like the PCB has improved my snake playing skills, but yeah, all works. This may be the last time we see Snake before we get something more interesting running on the VGA. I'll see you again soon.